Hello, we'll be discussing on chromatographic technique in downstream processing in this class. Basically, we'll be discussing on the introduction for the chromatography. We believe that you have already some fundamental idea, you know how the chromatography things works, but we'll have some recapitulation on those topics probably in this day. So you can see in the right hand side one column chromatography rather will saying the purpose is to separate out maybe more than one or two compound in a mixture which is being loaded over a stationary phase which is actually adsorbent, and we are adding some mobile phase here, some liquid solvent, and essentially you can see in stage wise manner the compound is being separated. The separation reason can be the difference in their affinity or binding to the stationary phase, or maybe the compounds are as having different partition coefficients, they are moving in a different rate. So finally compound 1 or compound 2 can be separated out of the column, they're coming out in a different time frame. So basically we are exploring the differential interaction of solute between mobile phase and stationary phase. So at any time there are three components in a system we need to really care for. One is the stationary phase, which is going to bind your analyte, maybe your target analyte, and which is non-desirable analytes as well. And when we are passing this mobile phase, so analyte which has already interacted with the stationary phase will now partition into mobile phase. So some component is coming back into mobile phase depending on their partitioning behavior. Molecules which are having weaker interaction will move with the mobile phase, whereas those who are binding strongly with the stationary phase will stay for a longer period of time, which is generally expected here. And the phenomena is guided by partitioning, as you already told, that is solid liquid phase partitioning of your compound. So it is very similar to adsorption process, of course in a localized manner, but there is some differences also. We don't really assume the adsorption is coming into equilibrium, that is already every moment it is going, it is not a equilibrium condition, rather transient state, because your solvent is being renewed every time the mobile phase is constantly being fed into the system. So that differences you should keep into mind, and different component of the mixture travel at different speed, causing them to separate. We use the word speed because the different amount of concentration, the different plume of your compound will come into the segregated portion in the solvent. So depending on the flow rate, different fraction of your compound can come out in the chromatographic process. Now basically what are the different kinds of classification in chromatography is available. So primarily we will classify this chromatographic technique based on how they are interacting with the support. In this class, or maybe in this lecture, we are going to discuss only in solid liquid separation process. So there is one solid stationary phase and the liquid phase or mobile phase which is going to interact with your target compound. There can be of different kinds of interaction over here. You can see the first one is gel filtration, which is depending on the size. So molecule may go inside the gel matrix, so depending on the size they will go inside. If the smaller particle can go inside but the larger particle cannot go inside the hydrogel or gel beads, we are going to interact. HIC, that is hydrophobicity, is the key player over here. Similarly the reverse phase also very similar with one another, but the fundamental procedure remains same. In reverse phase the degree of interaction is much higher compared to HIC. In both the category, the hydrophobic force is actually bringing them together. So hydrophobic interaction is the mechanism through which it is interacting. Ion exchange process is pretty simplified one. So positively charged binding site on the adsorbent is going to interact with negatively charged analyte. So because of the charge interaction they will be binding, and for biorecognition affinity based separation like antigen antibody kind of reaction, which is very more specificity in the molecular level, they can interact, that is known as affinity biorecognition chromatography. So basically, depending on the charge, size, hydrophobicity and biorecognition are the four domains which we can classify the chromatographic process. Though there are different other way of classification also possible there, like gas chromatography, liquid chromatography, which will be further classified into paper, column, thin layer. But you need to understand, for analytical purpose all those chromatographies may be important. But when you are discussing about downstream processing, we are assuming that preparative chromatography. So in case of preparative chromatography, gas chromatography will really have no values over here, because most of the compounds when we are using gas chromatographic technique, they are all volatilized, not likely to be recaptured over here. Um, Preferably we can have the liquid chromatographic technique, which is more widely used. Thin layer chromatography can be used for analytical purpose, and column chromatography, both analytical and preparative mode, we can use. So basically there are three components, as you already discussed. One will be one stationary phase, which is solid, a layer of liquid adsorbed onto the surface of the solid support, which is actually interacting. Maybe one kind of film is produced on the solid. Mobile phase is a liquid phase or gaseous phase, but for liquid chromatography we will be restricting our discussion in liquid phase only. And the molecule what we are going to separate, it is a mixture of molecules. So maybe compound A and compound B are all together. We will be discussing those aspects, how we are going to separate in coming slides. Now about the instrumentation part. Though this diagram showing instrumentation for HPLC, high performance or high pressure liquid chromatography, and basically the procedure remains same. Maybe in case of column chromatographic method it is little bit more simplified. Essentially in this case we can see the HPLC solvent is loaded through HPLC pump because of the high pressure requirement. It is going through injector, HPLC column and detector, and finally data acquisition. So once the system is in equilibrium, I mean to say when the solvent is already running through the column, a small volume of sample is injected through injector. So it is actually coming into the line, into the continuous flow, and the compound will be separated based on their affinity, or I will say interaction with the solid phase. When it is coming out, it can be collected or recovered, or maybe thrown out. If you are going to say it is a waste, then you can throw out. So this is the basic principle which will remain unchanged for any other kind of chromatographic technique as well. So solvent saturated stationary phase, injection, and finally you are eluting, because this is a continuous process. The solvent polarity or maybe pH will be changed, and the compound which is retained through injection process will be recovered, and finally it will be collected in a fraction collector, and the data will be acquired through a chromatographic methodology. So some of the statistical terminologies probably will be useful, or maybe in a chromatographic perspective or chromatogram we need to know what is retention time, what is hold up time, we will discuss it, and what is the corrected retention time, and we will have this diagram to describe all those phenomena. So this is a traditional chromatogram. when the when you are injecting the sample along with the solvent, the minimum time, because depending on the flow rate of your solvent and the void volume of your column, it will definitely take some time. Even if they are not interacting with the column material or there is no interaction, some minimal time will be required. Even the solvent has to come out through the column. During this time period, the minimum time period is known as hold up time. It is very simple to calculate. If you know the void volume and flow rate, it is simply void volume by flow rate. So depending on the column length, depending on the flow rate, the hold up time can be different. So this is, there is no interaction with the column. But another one that is called essentially the hold up time, T0. When your sample is actually coming out from the chromatographic system, we can find out the individual peaks separated out, and the time from the point of injection to have your peak maximum, that is called retention time, we can find out. So anyway, as you know, the T0 is always there in a background process, so it doesn't really correlate with the binding with the adsorbent or how much it is getting retarded, it is not reflected. So we can always have some corrected retention time, that is retention time minus T0, the time minimally required or held up time. If we subtract it, it depends on retention time depends on the nature of the stationary phase, what kind of mobile phase we are using, column dimension and flow rate all together. Now, few terminologies which are useful for analyzing chromatographic technique or to understand how much efficiency of the chromatographic process is there. Few terminologies including capacity factor or retention factor, which is actually normalized and is done. So actually the corrected retention time divided by the time required to come up the solvent, or you can say the void space time, the minimal time which you normally use. So TR minus T0 by T0. If the retention factor is going to be, for example, if I say the retention factor is 0, that means the compound is not being written, it is coming up with the flow without any interaction. So that time TR and T0 are same, that is called a retention factor of 0. But if it is 0 means this column or this chromatographic system is not useful for your desired compound. For practical application, the factor should be between 1 to 5. If the value is 0, as we already told, we cannot use it because it is not interacting with the column. But if it is very high, then it can take long time for eluting out the compound. So that is not really good idea because we need to run it for a longer period of time. And the second point is a separation factor, which is actually talking about, or which is actually discussing about separation of two compounds in a chromatographic system. If both the peaks are coming very close to each other, that means there is no separation, and the separation factor can be given by comparison of the retention factor. So if I say in the first case, if one retention time and the other retention time is too different, that means their separation is sufficient enough, or you can say they are sufficiently separated out. So essentially the retention factor ratio is going to give you a separation factor. So K2 prime by K1 prime, K1 prime and K2 prime can be calculated from the retention time data. So essentially it gives us the idea how these things are really separated. So we need to have separation factor, of course definitely more than 1, and expectedly within 1.5 or 2, so that the two peaks are really separated. And the last terminology which you can use for, or mostly we use, is the resolutions. So it actually gives you the same idea how the peaks are really overlapping or not. So T2 and T1 are their retention time, and W2 and W1 is the width of those two peaks. So if they are overlapping, so that time if they are just touching these two peaks, then we can expect that R equal to 1, or if they are crossing each other, in that case the resolution values can be even lower. Now we will be discussing about something on theoretical plate. Probably you need to understand theoretical plate concept is coming from a column, because you can assume the whole column as a array, a series of small segments which are actually interacting with one another in a continuous manner, like we have seen in case of liquid extraction process. The same procedure you can assume also here as solid liquid extraction, but in a constant manner, constant flow of the liquid carrying your compound. So essentially we can assume that each of the component is a plate. So basically this is a theoretical plate concept which is coming over here, and the Gaussian distribution of one peak and the variance of the peak, because if you assume it is a Gaussian distribution, we can calculate the variance also. The number of theoretical plate is actually calculated based on the retention time and the standard deviation or variance of the Gaussian peak. So number of theoretical plate is calculated is TR by sigma square, and the width of this peak at half height, that is called WB, is equivalent to 4 sigma because of the nature and equation of the Gaussian distribution. So we can actually simplify this expression for theoretical plate, that is 16 into TR by WB square. TR we already know, and WB we can calculate for a given specified condition of a column, and which can be further simplified TR TW as 1 by 4 square root of n. Now resolution, whatever we have earlier written in our last slide, can be rewritten once again. That is, resolution is coming from TR by WB, that is 1 by 4th root n, alpha minus 1 by alpha multiplied k by k plus 1. So here there are three different components which are actually giving the resolution picture, or we can control to have a better resolution. First one is the theoretical plate. If we increase the column length, we can actually increase the number of theoretical plates, but number of theoretical plates increment will have one consequences, one problem, that is the longer retention time. Now alpha is a separation factor. You can see alpha minus 1 by alpha can have a significant impact. If we change the alpha values, probably we can alter the resolution's values a significant way. And k by k plus 1, you try to understand that we are assuming there are two peaks. One peak we are keeping as a on hold constant, we cannot change that. We are talking about the other peak. So essentially, if I am changing for one compound perspective, keeping the other one as constant, so k is coming up from the concept that partition coefficient, which can be controlled by changing the solvent specifically, where we can have a more control on k values for a compound. So we can have three different controlling points. Specifically, we can see alpha minus 1 by alpha will have a significant impact preferably, and in the other sense k by k plus 1, if we do, the impact will not be so great as expected from this analysis. So you can have a better resolution, better separation of your compound, depending on how you are going to maintain the chromatographic system. We'll be discussing the other details of different kinds of chromatographic methodology in next class.